Hello and welcome to this basics video regarding the OSI and TCP stack model for network. If you enjoy the content, give it a like and subscribe. I do game streaming when I have free time and post cybersecurity basics videos, paper reviews, and anything interesting like tutoring sessions I do with consent of the person I'm tutoring. Today I'm going to discuss the two types of stacks, the TCP IP stack and the OSI model stack. They do overlap, but they do have nuance. Let me know in the comments if you took a class or you are currently taking a class and you find the explanation I'm giving to be better than what was covered in the class. That being said, let's go to the slide. There are two network stacks. On the left here we have the TCP IP one, and on the right we have the ISO. The TCP stack has 5 layers, 1, 4, 5. The ISO has 7, 1, 6, 7. Seventh one's cut off. Don't worry about that one. And TCP IP, we have application transport network, data link, and physical, whereas in the OSI, we have application presentation session, transport network, data link, physical. The main difference between the two is that the OSI model has presentation and session, and for the OSI model, which you'll see later, this actually makes more sense to have the presentation and session in a different layer. As someone who knows not to trust software, having something to hold a presentation and or a session, having it so the application does not have to directly control that, in my opinion, creates a better sense of security. So let's start from the bottom up on the TCP IP stack. Here we have the physical layer, which is basically the media used to connect nodes on the data link layer. This could be fiber, copper, general twisted pair, or even RF. This is a point-to-point connection and does not have any smarts to it. Next, we have the data link layer, and if you notice on the slides, they're controlling the same thing, which is my biggest gripe with the TCP stack. But the data link layer includes MAC addressing for network interfaces. It also verifies that incoming frames, which is what the data is set on, have the correct destination MAC address as well. Routing can be done on this layer using media access rules. By the way, MAC media access control. So it receives packets from the network layer and encapsulates them to create data frames when sending, and when receiving it reassembles the frames for the packets it's receiving from the network layer. This may also allow for frame error detection using cyclic redundancy code, which if you're interested, let me know in the comments. I'll go over that. The transmission and data is received in bit signals. This layer defines signaling for the transmit bits, be them electronical, photons, or RF. This layer also has definitions for media and connection for media to accomplish network connection. The data link layer is also point-to-point. Its job is to ensure segments get from one point to another using routing addresses, namely MAC addresses. This isn't a fun layer, but it's more of a backbone one. Hardware found on this can be switches and routers acting as switches. They're basically dumb. Next layer we have is the network layer, which defines and verifies IP addresses, routes packets through a network resolving the MAC addresses from the IP addresses, and delivers packets efficiently. The network layer is where routers acting as routers come in. This would be pointing to a different direction and assigning IP. If you don't know, routers, when you're sending a packet out, will determine where the packet is headed on the routing table, and then just go, okay, this falls into this IP rule, I'll send it this way, this is a different IP address range, I'll send it a different way, etc. Mind you, if you are sending packets over the network, the data will have fragments going from network switch to network switch without being decoded, but if the fragment hits a router junction where it has to decide which routing path to go, it will go up into the network layer and have the destination parsed and then put back into the network fragments and re-encapsulating it to send it on its way. The network layer uses IPv4 and IPv6. ICMP controls like ping, ARP, which handles the request of MAC addresses from routers, and any form of IP security. The next layer up we have is the transport layer, which works in segments and provides a means of identifying the source and destination IP for applications in a communication session, and has a data protection checksum, which is used to ensure that the data wasn't corrupted while in transit. This layer gives us ports, so if you're used to port 443 for standard HTTPS traffic, this is where that port comes in. They are used with destination and source, where the sender has a source port, which is where the destination will send information back to. Ports like 443 are used as standard open listeners on server, but active sessions may end up on higher ports for both sessions, so that new requests can go into port 443 on the incoming server. The last layer on the TCP stack is the application layer. This layer is like a mixing pot of everything. Once the network traffic goes behind ports, so to say, contains kernel, network services, and user application customization. Most of the activity on this layer comes from user applications such as web browsers and the newest version of the RuneScape kids are playing these days. This also includes application session management. Session is when you securely connect to a website using SSL. When you're playing that RuneScape, this is how the server knows you're still connected. This layer also has protocols for authentication and data forming services. You'll notice when I am going over the OSI stack how these work. Other parts of the application layer involves access by an application to network-based services. These can be clients or servers for data access, name resolution like DNSSEC, and DHCP on the router, which is in the application layer because the computer is asking the router for an open IP in its IP range, and the computer facilitates the coordination. But DHCP is a higher level complexity that the router may use. It also does authentication and logging in, which is session management, and data formation and translation, like running a script to convert formats. Like when I'm sending out an email, the email is in HTML with pictures and whatnot. It needs to simplify that for the IMAP protocol and send it out and encrypt it and encapsulate it down the list. Next up, we have the OSI model, which may make more sense. The lowest layer on this model is the physical layer, like with the TCP model. As I said in the TCP section, this is for network media like fiber, copper, and RF. It also covers hubs and repeaters, which are used to fork or extend the medium. This also has connectors like RJ45, SPDIF, fiber terminators, cable caps, etc. because those are part of the physical connection. How do you get into the network interface without having a media connector? This layer also manages hardware connections. It handles the sending and receiving of bits on the line and handles how they are encoded, like a cable signal for DOCSIS 4.0, can also do RF propagation or photons in case of fiber. The next layer is the data link layer, which is also in the TCP stack. Data is transmitted here in frames. This includes Ethernet networking and network interface card drivers, which will call NICs. Some outdated things like token ring networking and FDDI. The layer you will find, on this layer, you'll find devices like network switches, which are smart enough to pick which direction they'll send the frame onto another junction, and the network interface cards. The layer provides physical device addressing, device-to-device delivery of frames, media access control, MAC addresses, which are associated with any type of interface card for a network. The next layer is the network layer, which is also in TCP. It handles packets. This is IP traffic, ICMP commands, which are like pings or trace routes, and ARP. You can find routers, firewalls, intrusion detection systems, and layer 3 switches on this layer. This handles packet routing, logical addressing, access control via packet inspection. Routers and layer 3 switches do need to look at the IP packets to know where they're going to be sent down the network. To accomplish this, it has to remove the headers from the previous 2 layers and then put the headers back in correctly so it can go through and find its way to another switch or router. The 4th layer is the transport layer, and this is the last layer that has a one-to-one comparison with TCP. The unit of this layer is the network segment. In this one you can find the TCP or UDP headers for the data, and it determines how it's going to be ingested further up. This ultimately ensures delivery of data. It breaks the data up into segments so higher layers can have an easier time parsing, though this could be considered a chicken and egg argument. Do we have the transport layer setting up the packets for easier ingest, or do we have the upper layers breaking up a segment for easier sending? But this layer does do the sequencing of the segments and any acknowledgement steps like the QUIC or TCP handshake protocols, and performs some flow control using the TCP, because UDP just throws everything at the wall and see what happens. The next layer up is the session layer, which is one of the functions that the application layer does in the TCP stack. This layer does DNS security and SSL connection, including things like SSH. Its purpose is to establish, maintain, and coordinate communications between application hosts. Examples include secure browsing to server services and logging into an MMO. The 6th layer is the presentation layer. It does redirectors, which are, if you're looking on a server, like a 302 redirect to point an address to a new location. This is something that the application itself does not know about. However, the networking hardware on the server does. You can typically find this in an HT access file on your server. The function is to handle data representation to applications and data conversion, including ensuring that the data can be read by the receiving system. And this layer also handles encryption and decryption, which wasn't the original intention, but this was the best part to drop it in, since the top browser itself would be rather cumbersome if you were dealing with looking at encrypted data and decrypting it in that one as well. Technically, you could work in encrypt data, but there are some data encryption standards where you'd probably have 100% likelihood of corrupting all your data if you messed with it. The last layer is the application layer. This layer handles HTTPS, SFTP, IMAC, POP3 Secure, and the establishment of DHCP connection. These are the high-level functions. You can think about this layer being responsible on your end, and for the video you're watching and listening to the audio, because this is where HTML5 ends up being rendered. It also has to be here since data going from YouTube to you is encrypted up until you hit this layer in your computer, thanks to that padlock icon next to the URL and the certificate on the site and your machine. Without the encryption-decryption layer below, you would see a bunch of junk instead of this video, which I hope is junk. Keep in mind, both models, you start from the topmost part of the layer, work your way down, send over, and you may find yourself going up and then down and up and then down until you hit the server where you go from bottom, go all the way up to the top again. Also keep in mind that everything above the network layer is technically on your computer, and if you ever attempted to set up a pfSense, like my friend Sebi has, you'll notice that the computer can operate as a router because it has the smarts. Routers have CPU. But the main idea is once you get anywhere in the stack, it can run in the PC, and this is why your computer and even your mobile phone have MAC addresses. It's not just for small network hardware. Anywho, if you have any comments, questions, leave them below, and thank you for watching. Have a good one. Peace.